Welcome to today's paper reading. Today's paper is titled, The Illusion of State and State Space Models. This paper, published in the Proceedings of the 41st International Conference on Machine Learning, explores the limitations of state space models by William Merrill and colleagues from New York University and the Allen Institute for AI. The abstract discusses the comparison between state space models, SSMs, and transformers. SSMs are designed to handle sequential computation and state tracking, which transformers are not capable of. However, the analysis shows that SSMs, such as S4 and Mamba, have similar limitations in expressive power to transformers. This means they cannot solve simple state tracking problems like permutation composition. Experiments confirm these models struggle with state tracking, indicating that the state in these models is an illusion. The abstract concludes by suggesting that a minimal change could enable SSMs to express and learn state tracking, thus motivating the development of more expressive SSM architectures. Figure 1 illustrates the inability of state space models, SSMs, to address inherently sequential problems such as permutation composition, S5. This limitation is critical in various state tracking scenarios, including the tracking of chess moves using source-target notation, evaluating Python code, and monitoring entities. Consequently, SSMs are generally incapable of handling these tasks, highlighting their theoretical and practical constraints in managing sequential data and state transitions. Recent theoretical work has demonstrated that transformer-based models are unable to perform inherently sequential computations. This limitation is significant as transformers cannot handle simple state tracking problems that even basic recurrent neural networks, RNNs, can manage. In contrast, state space models, SSMs, have been proposed as an alternative to transformers, aiming to achieve RNN-like capabilities for stateful and sequential problems. However, this work reveals that the stateful design of SSMs is an illusion in terms of their expressive power. Both linear and Mamba-style SSMs, like transformers, are incapable of expressing sequential problems, including state tracking. Empirical experiments confirm these theoretical findings, showing that both transformers and SSMs struggle with permutation composition, while RNNs can handle it with ease. This suggests that current SSMs do not have an advantage over transformers in terms of state tracking capabilities. Figure 2 illustrates the complexity hierarchy within NC1, highlighting the limitations of both transformers and SSMs in recognizing languages only within TC0. This figure demonstrates that these architectures cannot express the hard state tracking problems captured by NC1 complete problems such as S5. In contrast, RNNs can straightforwardly express these NC1 complete problems. The figure is based on the widely held conjecture that TC0 is not equal to NC1. The paper begins by introducing the state space models, SSMs, that will be analyzed. SSMs are a type of neural network architecture designed for sequence processing, similar to recurrent neural networks, RNNs, or linear dynamical systems, LDS. They are proposed to have advantages over transformers, such as faster inference and better expression of sequential problems. Several variants of SSMs have been proposed, including S4 and Mamba. The paper then defines a generalized linear SSM layer, which includes both recurrent and convolutional forms, and discusses the layer outputs and their dependencies. Two common cases of this layer are also presented, non-gated and diagonal. The paper also addresses the numeric data type used in the circuit complexity analysis, emphasizing the importance of efficient parallel computable operations and the distinction between finite precision and log precision floating point numbers. State tracking involves determining the final state of a system after a sequence of updates. This can be analyzed using circuit complexity and algebraic formal language theory. Specifically, state tracking over a finite world can be viewed as a word problem on a finite monad. Different updates correspond to different elements in the monad, and the final state is computed as the product of these elements. This approach reveals which state tracking problems are likely not in TC0, indicating that models like SSMs cannot express certain hard state tracking problems. Notably, non-solvable groups, such as S5, have NC1 complete word problems, which are beyond the expressiveness of models in TC0. This section demonstrates that common variants of state space models, SSMs, can be simulated within the complexity class TC0. Specifically, it shows that non-gated SSMs, diagonal SSMs, and simultaneously diagonalizable SSMs can all be simulated in TC0. This implies that these SSMs cannot solve inherently sequential problems, despite their recurrent and stateful appearance. The proofs for these claims are structured around two main conditions: the ability to compute transition matrix products and the computation of individual matrices in TC0. Additionally, the section discusses the limitations of SSMs in terms of their expressive power compared to RNNs and explores extensions to SSMs through the introduction of nonlinearities and input-dependent transition matrices. The authors demonstrate how to extend the expressive power of SSMs, specifically S4 and S6, to handle problems beyond TC0, such as state tracking like S5. This is achieved through two key extensions: adding a nonlinearity to transform the SSM into an RNN, and making the matrix AI input-dependent, which aligns the SSM more closely with a weighted finite automaton. These modifications enhance the SSM's capabilities while potentially reducing parallelism. Theoretically, these extensions allow IDS4 to surpass TC0 limitations, enabling it to simulate deterministic finite automata and recognize regular languages. However, practical considerations include the need for parallelism in large language models and potential issues with learning dynamics, such as gradient vanishing or exploding, which could affect the model's performance. Figure 3 illustrates the minimum number of layers required to achieve over 90% validation accuracy on group multiplication problems, categorized by sequence length and group. Notably, RNN and IDS4 models demonstrate the ability to solve arbitrarily long sequences with a constant depth, whereas Transformer, S4, and Mamba models exhibit a requirement for depths that increase monotonically with sequence length. The task involves modeling word problems as a token tagging task, where models are given sequences from groups like A5, A4 times Z5, and Z60, and the label at each step is the product of the first I elements of the sequence. The models tested include a transformer as a TC0 baseline, an RNN expected to perform state tracking, and 3 SSMs, S4, Mamba, and IDS4. The experimental results show that single-layer RNN and IDS4 models can learn the word problem for arbitrarily long sequences, while Transformer, S4, and Mamba models require increasing depth with sequence length. Despite this, S4 and Mamba appear to be better at approximate state tracking on non-commutative tasks compared to the Transformer. In this paper, the authors formally analyzed a family of generalized linear state space models, SSMs, and demonstrated that, similar to Transformers, common SSM variants such as S4 and Mamba are limited to the complexity class L uniform TC0, which is highly parallel. This limitation means they cannot solve inherently sequential problems like graph connectivity, Boolean formula evaluation, and the permutation composition problem S5. S5, which is NC1 complete, can be naturally expressed by true recurrent models like RNNs, highlighting their superior state tracking capabilities. In practice, one-layer RNNs can easily learn tasks capturing S5, whereas linear SSMs require increasing depth with sequence length. These findings suggest that S4, Mamba, and related SSMs cannot truly track state but can only solve simple state tracking problems with shallow shortcuts. On the other hand, an input-dependent SSM similar to Liquid S4 can both express and learn the S5 word problem, indicating that the expressiveness limitations of current SSMs can be overcome. This research could lead to new neural architectures that balance the parallelism of transformers and SSMs with full expressive power for state tracking, potentially enabling large language models, LLMs, that benefit from scale while enhancing their reasoning capabilities about games, code, and language. Thank you for watching.